Hello everybody and welcome to today's lesson on graphing rational functions. In fact, the first of two lessons on graphing rational functions. The objective for today is we will graph rational functions using our well-known transformational approach, and we will investigate and analyze those rational functions graphically. So let's start off with our parent rational function, and that function is f of x is equal to 1 over x, with x in the denominator. And remember, to start off, we always use our key values, plug them in to see what the function is going to do, to get an idea of what that function is going to look like. If we plug in -2 for x, we get 1 over -2, or in other words, -1/2 for f of x. If we plug in -1, we get -1 over 1, or just -1. If we plug in 1 for x, we get 1 for f of x. And if we plug in 2 for x, we get 1 over 2, or 1/2 for f of x. Let's start marking these points in our coordinate plane. -2 and -1/2 is going to be about here. -1 and -1 is going to be here. 1 and 1 is going to be here. And 2 and 1/2 is going to be here. So, but what happens if we plug in 0 for x? If we plug in 0 for x, we get a denominator of 0. We can't divide by 0. This is undefined. Remember, we can never divide by 0. That's undefined. Then we cannot use that point for our graphing purposes. That's a shame. So what is our graph going to look like then? Well, here's what we're going to do. We're going to take a look at our calculator and see what the calculator says. Putting in y is equal to 1 divided by x, and let's see what a graph looks like. Whoa, that's interesting. So we get two lines, they don't connect. And can you see how the two lines get very close to the x-axis to the left, very close to the y-axis on the bottom, very close to the y-axis again on the top, coming from the right, and very close to the x-axis as they go off to positive infinity. Okay, that helps, so we can now sketch our lines the way they should look like. This is what the graph of the parent rational function looks like. And very importantly, please note that those two parts of the graph, they will never cross or even touch the y-axis, because we cannot have a value that divides by 0. And they will also never touch the x-axis. And here are two new concepts that we will use now. Those dotted lines that I have put in here, they are called asymptotes. Asymptotes are lines your function approaches but never touches. And we have two different types of asymptotes. We have horizontal asymptotes that describe the end behavior of your graph. And we have vertical asymptotes. They describe where the graph grows without bounds. In other words, where it goes to positive infinity and negative infinity and always keeps going. For our parent rational function, what are those asymptotes? The horizontal asymptotes are lines, so we can give them equations. The horizontal asymptotes is y is equal to 0. Remember right here, y is equal to 0. It's essentially the x-axis in this case. And the vertical asymptote is a vertical line, so x is equal to 0 as well. And that is where a graph was undefined. So since we want to graph all rational functions using a transformational approach, we need to understand how A, H, and K change the graph of any rational function. And A, H, and K are in these positions. Y is equal to A over X minus H plus K. And here we have an example, and so now let's use that example to graph and to see what A, H, and K actually did compared to our parent function. First, we're going to start off by determining what are going to be our asymptotes. First of all, a vertical asymptote has to be wherever the graph is not defined, because we ended up with a fraction with a denominator of 0. Where will this denominator turn to 0? If x is positive 3. That we can't have. So our vertical asymptote is going to be at positive 3. A horizontal asymptote, well, remember k moves our graph up or down. And if k in this case is positive 1, then the entire graph is going to be moved upwards. And that is where our horizontal asymptote will be. So we can already note this down. We have a vertical asymptote that is x is equal to 3, and a horizontal asymptote that is y is equal to 1. When we want to graph this, since our dilation is positive 1, we can use the same points that we found for our parent rational function and mark them off relative to the intersection of our two asymptotes. When we went 1 to the right, we went 1 up. When we went 2 to the right, we went 1/2 up. When we went 1 to the left, we went 1 down. And when we went 2 to the left, we went 1/2 down. And that lets us graph the two parts of our hyperbola. So what is the domain? X, such that x is not equal to 3, where we have our asymptote. And the range is y, such that y is not equal to positive 1. Let's look at our end behavior. As x goes to negative infinity, f of x goes closer and closer to positive 1. And as x goes to positive infinity, f of x also will get closer and closer to positive 1. Our parent rational function does not have x or y intercepts, but other rational functions do indeed. So let's find our x and y intercepts. Start with the y-intercept, and that we find when we plug in 0 for x. Y is equal to 1 over 0 minus 3 plus 1. In other words, 1 over negative 3 plus 1, or negative 1/3 plus 1, which is 2/3. 0 and 2/3 are the coordinates. And if we look here, that is pretty much exactly where we put our point. And the x-intercept we find if we plug in 0 for y. Then we can say 0 is equal to 1 over x minus 3 plus 1. Move the 1 to the other side. Negative 1 is equal to 1 over x minus 3. Now we're going to multiply everything by the denominator, and we get negative 1 times x minus 3 is equal to 1. Distribute our negative 1. Negative x plus 3 is equal to 1. Subtract 3. Negative x is equal to negative 2. And now we divide by negative 1 to get x is equal to 2. 2 and 0 are our coordinate of the point that we have right here, and that is our x-intercept. In our next example, the dilation is actually not 1, it is -3, which means that this time we will have to plug in numbers to find points and graph those. But first things first, let's find our asymptotes. The vertical asymptote is where the denominator turns to 0. In other words, x is equal to -5. And our horizontal asymptote is where our k shifted the whole graph up 2 steps. In other words, y is equal to 2. -5 is our vertical asymptote, and +2 is our horizontal asymptote. Our domain is x such that x is not equal to -5, and our range is y such that y is not equal to 2. Let's talk about our end behavior. As x goes to -infinity, f of x goes to 2, and as x goes to +infinity, f of x also goes to 2. We can already say that without having even graphed our hyperbola, because that is what is going to happen around our horizontal asymptote. Let's find our intercepts. The y-intercept will be y is equal to -3 over 0 plus 5 plus 2, which is -3/5 plus 2. 2 is 10/5, so -3/5 plus 10/5 is equal to 7/5, or in other words, 0, 7/5 are our coordinates. 0 and 7/5 is a little less than 1.5, so somewhere up here. Our x-intercept, where y is equal to 0, 0 is equal to -3 over x plus 5 plus 2. Moving the 2 to the other side, -2 is equal to -3 over x plus 5. -2 times x plus 5 is equal to -3. Now we distribute, move the 10 to the other side, and divide by -2. X is equal to -7/2, -7/2, and 0 are our coordinates. -7/2 is -3.5, so -3.5. That is our x-intercept. Now we need to find some x-coordinates, plug them in so we can plot more points. And those should be values which are going to be somewhat close to our asymptotes. So I'm going to start off with -2. F of -2 is equal to -3 over -2 plus 5 plus 2. In other words, -3 over 3 plus 2, which is -1 plus 2, or just 1. So for -2 we get a y coordinate of 1. And then I'm going to move a little closer to our vertical asymptote, and I'm going to pick f of -4, which is going to be -3 over -4 plus 5 plus 2. -3 over 1 plus 2. -3 plus 2 is -1. So at -4, we get a y-coordinate of -1, and that gives us this point. So we're pretty good for this part of a hyperbola, but we also need the other part. So I'm going to go 2 steps more to the left and find the y-coordinate of the point -6. -3 is equal to -6 plus 5 plus 2, which is -3 over -1 plus 2. 3 plus 2 is equal to 5. At -6, we get a y-coordinate of 5. And last but not least, I'm going to go yet 2 more steps to the left. F of -8 is equal to -3 over -8 plus 5 plus 2, and that's -3 over -3 plus 2. In other words, 1 plus 2, and that is 3. So at -8, which is just one step off our grid, we get a y-coordinate of +3. These are our points, and now we can go ahead and graph our hyperbola. This is one leg of it, and this is the other one. So let's just again spend just a second to remember and recap what A, H, and K do for the graph of our rational functions. A, as always, is the dilation. H is the horizontal shift, horizontal like H, and K is the vertical shift. Alright, so much for this, and now go ahead and watch the second part of this tutorial.